Welcome to another CO2 Monday in the Refrigeration Mentor podcast. As always, I want to thank you so much for taking the time to come and hang out with us here each Monday, 2 p.m. Eastern time, depending on where you're at in the world. It could be 8 p.m., it could be 6 p.m., it could be even a bit earlier. But what we're here doing is bringing top talent, CO2 experts from around the world. And this week, I got a great guest, my good friend that I actually recently met through Giacomo Favri, Marcel Nishimori. And we've been talking over the last week. I've been learning about the knowledge Marcel has. It's been blowing me away. Like, this guy's been in the industry doing technical support for over 10 years, leads a team of 9 people where they are supporting a massive country, a massive market, and heavily involved in CO2. What we're getting into today is a topic that I need to learn more about. And compressors that I've been hearing more and more about, seeing more and more in the market, continuing to grow. And I'm super excited about this conversation. Marcel, welcome to CO2 Mondays. How you doing, brother?
I'm doing very good. Thank you, Trevor, for the invite. I'm very excited in participating in your show.
Marcel, why don't you do an introduction of yourself and let the audience know a little bit about you and what you do?
Perfect. My name is Marcel Nishimori. I'm working for Carel for the last 10 years almost. I've been in different positions since technical sales for Latin markets. So we divide Carel here as Brazil and extra Brazil. Every country that is not Brazil is considered extra Brazil and was where I learned a lot about CO2. I traveled all around South and Central America, visiting CO2 installations from 2013 to 2018. And then in 2018, I took the position here for the Brazilian market. And since then, I'm just evolving and learning about CO2, about transcritical stuff, compressors, inverters, and so on. So here as technical manager, I have the responsibility of the technical support, as Trevor mentioned. I also taking care about the R&D for hardware units. That's one of these, and also for software development. So we do a little bit of everything here. We are a very lean team, and everybody needs to know a little bit of everything. So this is our philosophy here in Carel, South America.
What I love about that is that it gives you more knowledge on different things. Learning a little bit about a lot of things will help out. You always want to get to your knowledge level where you're mastering a lot of different things and then adding to it. This is what you need to do. If you're out there in the field, if you're a technician, if you're an engineer designer, if you're a planner, whatever you do, you want to continue to evolve and continue to learn, just like Marcel. And putting yourself in those situations as well, getting outside your comfort zone. I am sure you've been there many times, Marcel, trying to figure out these products with customers, because you guys develop new products. You do the R&D and you got to go see it at the forefront. And sometimes it's like, oh, this is not working. Oh, this is working great. And you got to come up with a solution. How has that been, learning and transitioning your role over the years, getting to where you are?
It was a very challenging situation because as our culture, Carel develops a lot of products, and we keep saying to people that if you want to join Carel, you should be a constant learner, because every day, every year, Carel launches a new product, a new technology, a new solution, and you need to catch up as it goes. So we learn a lot, and we always are very pushed to learning new things and going through this natural solution stuff. This is very fun, Trevor, because I always say to my people that when you are in installation, automation, and it's almost the last phase of the commissioning. So you are running everything manual. So now we are going on automation controlling. So you need to be there, and the system must work. And if something goes wrong, it is the controller side that is the guilty of the system. So we always are pushed to give our best, because there are always some product arriving. You are in a hurry to make the unit running, so it's a very challenging ambient. But this challenge makes you learn, makes you stronger, makes you understanding in deep the solution. You are not just the controller side. You need to understand a little bit of mechanical thermodynamics in order to understand if your problem it is really something from the controller side, or is a bad probe, a bad transducer, or something that is not reading correctly and is making that the unit is not performing well. So you need to acquire these different knowledge and understand the application. I tell my people that even they are customer support for electronics, as our main business are, we need to understand our customer application. So we need to understand how the unit should operate, how it is the right way to operate in order to make the changes and adjust when needed to make it run in a smoother way.
Yeah, and when I talk to so many different controls manufacturers, electronic manufacturers, you have to be better at refrigeration than most people out there because a lot of your calls, I know for sure you haven't told me, but I bet a lot of your calls are more on the mechanical side. When you're getting a call, it's a mechanical issue, but they're calling you because it's your controls on there, your electronics. Because I talk to all these control companies and they're like, Trevor, I am troubleshooting the refrigeration mechanical side more than the control side when I get these phone calls. A lot of the phone calls anyway. Do you feel that way as well?
Yeah, this is the how we operate. Like we try to understand first what is the type of application customer is doing, which kind of compressors or which kind of system they are trying to fix. What is the problem? Not it's in general we receive very generic calls. Oh, my unit is not working. Okay, your unit is not working, but specifically it is the evaporator that's not working, it's the compressor that's not working, it's the valve that's not working, and then we start to collect information from the field. What is the super reading? What is the pressure you are reading? What is the evaporation temperature? What is the evaporation pressure? And you start to correlate information and make your analysis in order to understand what could be the problem. If it's a parameter, if it's something that went bad, it's a challenge. You need to really start to imagine how it is the equipment in front of the technician and try to make the connections and understand what could be the problem. And based in your knowledge and the previous supports, you start to correlate things and say, okay, it might be a temperature probe that is not insulated and is reading a higher superheat, and then your valve is opening too much and you are having liquid back to the compressor. But it's a correlation of facts, and sometimes not the controller that is bad. It is something, some details that it is missing that makes the whole unit, the whole system stop working or having trouble in the middle of the night. I know that our application refrigeration is a critical mission. You cannot stop. Otherwise, you are losing food, you are losing money. So it's a very tough, it's a very challenge ambience.
Yeah. And that exactly what you said there. And this is everyone needs to do. You got to take a systematic approach when you're troubleshooting. This is why they'll ask you all like Marcel's team will ask you certain questions. And you're like, why are you asking me this question? Well, they want to make sure that they go through their checklist. They'll have a checklist that they're going through and they're like, oh, they're just reading off a document. Yes, you need a checklist. When you're doing troubleshooting, you need a systematic approach so you don't miss anything. Just like Marcel there, you miss one thing. That's why the system's not running properly and you miss that. And then an hour later, you get back to it. Oh, it's this, it's that probe that wasn't insulated, for an example. Taking a systematic approach when troubleshooting is so important. Before we get into the compressors, what are some of the top calls that you get for either the unit that we're going to talk about that's in front of you right now or your electronics? Do you know a few off the top of your head?
Yeah, sure. Most of the times, the most common calls we receive are related to probe bed readings. So it could be an electrical issue, like I have a temperature probe and it is disconnected because it's vibrating or something like this, and it's giving us a bad reading. So try to understand first what could be which kind of alarm, listing it, and then understanding the type of probe. Try to measure. Sometimes with a simple meter, you can check if a temperature probe is bad, is broken or not. So it's a simple procedure that you can do on field and spare a lot of time on analysis. This temperature probe is something that we receive a lot of calls. Electronic expansion valves are our top calls also. So customer sees an electronic expansion valve. He is very used to make and do adjustments in thermostatic ones, and he's a little bit afraid when he. So when we teach our technicians that there are a few parameters that they need to check, the type of probe, type of valve, set points, and then so on and so forth, they get more comfortable with the situation and start promoting it. So valves is something that we receive sometimes some calls. And on the unit in special like this one, what we receive from calls is like sometimes for the technician it's not so easy to understand the PNID logic. So he says, oh, my unit is, the cold room is under temperature, but the unit keep running. Why did it is not stopped? And we start to explain how a PNID logic works, how the compressor accelerates and deaccelerates in order to maintain temperature. Most of the times, my team here are more like explaining how the system works, and technicians start to make the correlation, and they get and they understand, and they are very independent once they understand how it works. We like to say that we try to teach every time we are doing a customer call. We are trying to teach them how to do our approach. We are not hiding anything, and we don't have a secret book with all the answers. We, as you mentioned, we have some checkpoints we start doing, and once they start to do this before calling us, sometimes they neither need to call us. This is just a matter of checking these steps and make the correlation. So it's a process that we try always to make it run.
Yeah, and that's exactly right. Every time, and most technical support people that I know, they are trying to teach a little bit, because a lot of the people that do call in may have not seen it before. Maybe didn't have the manual there. Someone took the manual away. They got to figure it out. It's not like a mechanical device. And I've talked to almost all the electronic valve manufacturers, and I know so many people. There are so many of them being replaced, the valve itself, and that's not the problem. Oh, the valve's not working, it's not open, it's not closing, let's cut it out. All manufacturers I talk to, they run into that issue. After that person learns about how to properly set it up, commission it, you don't see as many electronic valves replacements. So, Marcel, thank you for talking about that. I think that's so important. We should do a whole session on just how to troubleshoot a system. But let's dive into these compressors, because I am super excited to learn about these twin rotary CO2 compressors.
Perfect. Let's go into that. So first of all, when we are talking about BLDC technology, what BLDC means? BLDC is an acronym for brushless DC technology. It is more related to the motor of the compressor rather than the compressor itself. We are used to say that these BLDC technologies are kind of a motor that goes inside the compressor and makes the name of the technology. BLDC, why? Because when we have a general motor, a traditional motor, we have a rotor and a stator that you need to induct some current in order to generate the magnet field. And this magnet field running that makes that the movement of the rotor. In our case, in specific, we do have a permanent magnet into the rotor. So instead of inducting the current inside the rotor, we have a permanent magnet. It's a rare metal that we use for these rotors, and it already has the magnet fields already built in inside that. That you don't need to generate you don't need to put the current inside. And as you don't need to put the current, you don't need the brushes that are the carbon parts that makes the connection between the movement parts and the stator. And you just need to generate the magnet field on the outside part on the stator. So in this way, we start saving a lot of energy and making the unit more efficient in this condition, because you don't have a friction, you don't have the loss for heating, and so on. So BLDC, it is the type of motor we have inside the unit. And considering that BLDC are a technology that was made to be variable, so it is mandatory to have an inverter or a driver like this one to make the compressor running, because since we don't need to inject the current in the rotor, we need to know exactly the position of this rotor in order to make the magnet field on the outside. So we need the inverter. And since we have the inverter, we can modulate the speed of this compressor. BLDC technology are well known because we can have a very wide range of operation. Traditional motors, well, it is when you have a compressor and you have inverter that will drive this AC motor, you have some limitations on the modulation mainly because of the lubrication of the movement parts inside the compressor. The BLDC technology was a type of compressor that was designed to be variable. So we don't have directly strings related to the speed of the compressor and the lubrication part. I will show you later how it goes. And since we have this condition, we can have the compressor modulating in a very wide range. Here in the graph, just as a comparison, I can show you how a performance of on-off motor, a fixed speed motor, and a variable speed motor goes under different cooling loads. You can see that at 100%, when the application needs 100% of the cooling capacity, on fixed speed motors are more efficient because you don't have the inverter, you don't have any component in the middle of the electrical power and the motor. But when you need some modulation, variable speed compressors are more efficient than the fixed speed ones, as we can see here. And luckily for us, luckily for the people who promote the BLDC technology, the cooling loads most of the times are in partial loads condition. I mean, if you think about a cold room, during the day you are putting a lot of products, you are opening the door and so on and so forth. So the cooling load is very high. But during the night or in a colder day, the cooling load will decrease because you don't have so many door openings, you don't have so many product changing. So the cooling inside the cold room will decrease. And it is in this point where we can match the better performance of the compressor and the partial load, so where we gain more efficiency. And this happens quite often during the operation, like 46% of the time.
Wow. That's super impressive.
Yeah, this is how it is. If you take a supermarket or retail store, it is not at full load the whole day. It is for a few parts of the day after a defrost or when you are loading product inside the cold room or the showcase, but not all the time. It is where we make the difference. Talking about the mechanical construction of the compressor, BLDC technology, and mainly these rotary compressors we are seeing, they have a different logic or different approach. Traditional compressors are you have the suction line that goes under the compressor. You cool down the motor with this suction gas. It goes to the carter of the compressor and then goes to the compressor chamber and then directly to the discharge line. Here you can see it going on the discharge line. And this what makes it makes that you are very sensitive for any droplet that could come back from the evaporator. So if you have any droplet, it will mix with the oil inside the compressor and you wash out the compressor. So you will lose all the oil and starting to have mechanical problems inside the compressor. On the other hand, when you have a twin rotary compressor with a BLDC technology, they have a different approach. We have our suction line going into the compressor directly into the mechanical on the compressor chamber, so where the compression occurs. All these mass of the compressor are at the temperature of the discharge of the compressor. That's why we call a high pressure shell or a hot temperature shell, because the compressor is very hot. It's a different approach. If you have a few droplets that could come back from the compressor, from the evaporator, sorry, it will instantly evaporate because there is a huge mass of compressor at a higher temperature and a few droplets at low temperature. And this mix will make that the refrigerant will evaporate automatically. Then the refrigerant goes into the compressor shell. It hits the shell of the compressor, and this shell makes as a first oil separation. So if the refrigerant plus the oil will hit the shell, the droplets will fall down, and the refrigerant will keep going inside the compressor. The discharge temperature of the refrigerant goes cooling down the motors. As you can see, this is a motor that can operate at very high temperature. We'll cool down the motor at this discharge temperature, and then the refrigerant flows to the discharge, to the condenser, or to the gas cooler. So there are these a few differences.
Like, okay, so because I'm used to always working with low pressure shell compressors. So like for years and years, mostly I worked on a Copeland scroll. So that would be a low pressure cell. I know a lot of people that use the Copeland when it's low pressure. But now we're talking about this whole body, the whole shell of it, we're high pressure now. So now it's all that discharge. What is your check? Like one of the things that you'll have to do on low pressure, you always want to check your discharge temperature on the discharge line. Usually on the Copelands, it's 6 inches down. I teach on this one here. What is your discharge temperature check you're looking for, and what temperature would you guys recommend to make sure you keep below?
Okay, yeah. This kind of compressor in general, they are rated to work in discharge temperature around 100 degrees Celsius. So the discharge temperature should be around 100 degrees or below. So we have some protections inside the software that keeps monitoring the discharge temperature, for example. And in case of higher discharge temperature, we start to, or in some cases, decrease the speed of the compressor, reducing this temperature, or in other cases, in some specific models of compressor, not for CO2, unfortunately, we can vapor inject some refrigerant inside the compressor in order to cool down the discharge temperature. So we keep monitoring, and we have some thresholds where we start to first decrease the speed of the compressor, and if this temperature doesn't decrease at all, we stop the compressor in order to protect the compressor.
I love it. Oh, I can't wait to get into that part because I know you were showing me some stuff on your inverters and the Carel drives with them. So, okay, let's keep going. This is awesome.
This is our technology with the high temperature, high pressure shell compressor. And one last part that makes for me the most impressive part of this compressor, it is we have in general our compressors when it is vertical, the compressor chamber on the top of the compressor. So we need to make the oil going from the carter to the compressor chamber in order to lubricate all the parts of the compressor. In a traditional compressor, we have some kind of pump that is attached to the rotor. So the limitation is you cannot decrease too much the speed because you will have some lubrication problems. Here, since this compressor, this shell is pressurized at discharge pressure, and here we have our compressor chamber at the beginning at least at suction pressure, just by pressure differential, we can make the oil moving from the bottom of the compressor to the compressor chamber. This allows us to make the compressor running even at low speed without having problems with lubrication because the oil will always move just by pressure differential. So this is one of the key points for this kind of compressors. So here is a very quick video just showing how it is a rotary compressor skin. So you have an inlet from one side, and we have this movement part on the inside that keeps in contact with the shell of the compressor chamber, making the compression. Here at this other slide, we can see a better view of the compressor by inside. In this case, this is another type of compressor that has the liquid injection, as we mentioned, in order to cool down the discharge temperature when the superheat is very high, or you are dealing with a very big delta pressure, so you will need it. Twin rotary compressor has a very interesting characteristics that when one side of the one compressor chamber is doing the compression, the other one is relieving the refrigerant. So we kind of equalize forces, and we need a smaller motor in order to make this torque for the compressor. So the big advantage of having a twin rotary compressor is that we can have a double of displacement, and we do not need to have a double of the motor. We can have a smaller motor compared to one and to another. As you can see in the image, this is a twin rotary compressor that can be done like this one in horizontal installation. So we can decrease the size of the unit, and we can install it practically everywhere because you can operate with the compressor in a horizontal orientation or in a vertical orientation like this one.
Is there different things you need to look out for, Marcel, for that? So you have your vertical ones, and now you got horizontal ones. Is there different ways that you can run into issues with them mechanically because they're horizontal, or would be the same mechanical issues?
No, we don't have much difference in terms of mechanical stuff between one and another. What we do have is that for the horizontal one, we can see later that the envelope shape is a little bit more constrained than the vertical one. So we have some limitations, but for most of the refrigeration application, it is not a problem. It's just when you are working in a very extreme condition. But for the most of the applications, both of them can work properly for different applications.
And I like you brought that up, the envelope, because we're going to get into that in a little bit. But this is so key when you're working with these compressors, and especially if you're a designer out there, to understand where, or a technician, where that should be running. Because when you run outside those operation limits, that's when you run into issues.
Yeah, right. Envelope, we will go into that, but basically envelope is some conditions where the manufacturer ensures that the compressor can operate with no dangers for its operations. You can operate there for long, long time and with running with no issue, with no big issues. I will show you how it goes. So the balanced pipes, so we have increased efficiency because we have a smaller motor, noise reduction, and low vibration because basically we are always, all the time, splitting forces and summing up so you don't have a total force that goes in some directions. This is the compact dimensions between the models of the motor. And here, a very quick comparison between the different types of technology. You can see that we are in a very good shape with this inverter technology. We are just not as better as magnet ones, but magnet has its own limitation in terms of applications and capacities. They are very big compressors and rated for high temperature application, not for medium and low temp applications. And to do all this magic, we need some frequency inverters. We have different types of inverters, both single phases and three phases versions. Some of the motors, it depends on the type of the motor we are using, can be operated using a single phase 208 or 230 volts application. So for the US, you can just use two phases in order to make it running in a single installation. And some of the compressor, generally the bigger ones, we do need a bigger inverter or a three-phase application with 400 volts, where you can have a better displacement, a bigger displacement of capacity. Carel can supply for the Toshiba lineup all the inverters for these applications. All of them could be with cover, with no cover, with protective back protections or not. So we do have a huge family of inverters that could drive these compressors.
Yeah, when I was at the AHR show and I was walking through them with Giacomo, you guys have a huge lineup of different inverters, so it's good to see that. And then now you have options for OEMs who are designing their own equipment using your stuff, which is great.
Hey, I want to take a minute to talk about the upcoming Refrigeration Mentor learning programs. Every couple of months, we continue to roll out live instructor-led sessions by subject matter experts on compressors, supermarket refrigeration, and CO2 refrigeration. We're really here to help you grow. Get to that next level. Head to the Refrigeration Mentor webpage, refrigerationmentor.com. Check them out. See if this interests you. Read a little bit about it because we're really here to help you. These live sessions are for you to come and ask questions, to learn a little bit, to grow. We've trained thousands of technicians from 3 to 4 to 5 years in the industry, all the way up from 20 to 30 years in the industry. Either get them to the next level or get them back on track. Build that confidence, that knowledge, and that skill set. We'd love to see you there. We'd love to have you. Now let's get a conversation going.
Yeah, right. Thinking about the logics of the control, this is something that technicians and sometimes they have some doubts about how it works. Generally speaking, we have the demand that could be an information that comes from the unit itself, from the application. That is basically the comparison between our set point that we are working and or the pressure or the temperature that we are setting to work with that unit. That could be pressure controlled, the suction pressure or the temperature of the ambient. So it will generate some demands or some requests from the application. Once we have this information, the control will process this request and apply some filters based on the operation of the compressor. So basically, we will take a look and see if the compressor is running under the envelope, as we discussed, or out of the envelope. In the case that we are out of the envelope, we will apply some offsets and some filters in order to force the system going back to the envelope. So it could occur that you have like 100% request from the field, and your compressor is running at 80 or 70% of full speed, mainly because it could be related to some protections that our controller is applying to the system. And then this information is transferred to the inverter, and the inverter will drive the compressor. One of the key points I really like in this kind of solution is that our inverters, all of them are Modbus communicated to the controller. So basically, you need just to set up, for example, the type of the compressor you are using, and the controller will push back from the inverter will push from the controller all the parameters for that. So speed up ramp, speed down ramp, protections, current, and so on and so forth. So it makes the operation of the technician easier than going there and setting up parameter by parameters.
So you're saying, Marcel, if just say an inverter fails, you get the power surge, this could happen, someone puts the wrong voltage to it, whatever it is, and it fails. A technician, all they have to do is go into the Modbus, they'll put in the model number of the compressor. Is that what you said, or serial number?
Yeah, you take the controller. Inside the software, there will be an option for compressor configuration, and you can just select like I have a compressor for CO2 DY67, for example. So you set this compressor, and automatically the controller will send all the parameters to the inverter. So you can reprogram an inverter from the scratch with just few clicks. You don't need to have a table with all the parameters, all the information. We can have it downloaded by the controller. This is thanks to our laboratory where we bring all these compressors and we make a qualification for that. So basically, we map all the envelope and the electrical and the thermodynamic conditions, and we make available a list of safe parameters that we can run this compressor. So you can just simply type the model of the compressor you have, and automatically we will download all the parameters to the inverter. So for a spare part, if you need to change some damaged inverters, it is an easier way. Some of the new family of controllers automatically recognizes when it is connected a new inverter and automatically downloads. But let's say that the worst case scenario is you need to select just the model of the compressor and all the parameters will be fulfilled.
Wow, that makes life so much easier instead of, because sometimes you got 10 or 15 parameters that you have to put in. Sometimes it's even more, right? So that's awesome.
Yeah. Some of the other protections we have is like startup failure control. So basically, we send a command to run the compressor, and then we keep monitoring the probes, pressure probes. If the pressure doesn't go in a different way, so suction pressure goes down and discharge pressure goes up, in a few minutes, we will stop the compressor because something is wrong. It is not possible to turn on a compressor and you didn't see any pressure differential between suction and discharge. So we keep monitoring this in order to understand how this procedure it is failing or why it is a problem. So before burning the compressor, for example, we generate some alarms in order to have some technician to take a look on that. It is some protection we have. Another interesting thing is in order to make the current, the inrush current of the compressor lower, what we can do is equalize the pressure inside the system before starting up the compressor. So basically, we open the electronic expansion valve. That is general a feature that comes with the variable speed compressor with the BLDC. And we can simply reduce the pressure differential just for the startup procedure. So we make sure that the compressor we can start running with a lower current, and this can save a lot of the motor coil inside the compressor. So we do not force the compressor with a higher current to start up it. We can just make it very smoothly this startup phase.
So this pressure equalization, would that mean that the electronic valve controller or the case controller, the evaporator controller, whatever it is, will be communicating back to the inverter?
In some cases, yeah. So some cases we can connect the valves to the condensing unit controller or to the rack controller in order to make these adjustments. On other cases, we can have, for example, dedicated oil return valve to open for a few seconds in order to make this pressure equalization. It depends on the application, but most of them, we try in somehow to make this equalization before starting up the compressor so we can enlarge the life of the motor inside the compressor.
Yeah. That makes a huge difference when you do that, when you equalize the pressure, because just like you said, you put your amp clamp on. You can try this out in the field before a system starts up. Put the amp clamp on and see what it does when it starts up, and you can tell if the pressures are equalized or not.
Yeah, and we have some pressure control, as I mentioned. So we expect to see some pressure differential just after starting up the compressor. So we can make sure that this compressor is running and it's running for the right side. So it's like clockwise, it's not anti-clockwise, rotating the compressor. So these are some electronic protections that we can add. We can have when you are using BLDC technology. And last but not least, I would mention about oil management. I talked a lot of the benefits of having a variable speed compressor inside your system. You can modulate, you can energy save, you can have stability on the temperature. But on the other side, the only negative point I can see when you have variable speed compressor is that variable speed refrigerant means also variable speed oil dragging back to the compressor. So you need to take care about that. And this is one of the features we implemented into our softwares. So basically, when the compressor starts to run in a very low speed, so we can define a threshold for that, and for a long period, we just force the compressor to run at a higher speed to make the oil dragging back from the evaporators or from the system back to the compressor. So this can be done in parallel, for example, with the electronic expansion valves when they are connected together. So we can make sure that, for example, we can open a little bit the valves and accelerate the compressor in order to be really dragging back all the oil from the system back to the compressor. This is a feature that keeps monitoring the speed of the compressor and making these adjustments every time it is needed. You have a small variation on the temperature because you are changing basically the cooling capacity, but it saves your compressor for being without oil during the normal operation.
Yeah, that's way more important. Changing the temperature of a case is not as important as protecting that compressor because that's expensive. Where changing the temperature for a few minutes, so that all these parameters, like you said, will automatically be programmed through the Modbus when you put a new compressor in. We'll say so you don't have to change these parameters. Is that correct?
Yeah, it comes already embedded on the software. For sure, for example, some OEMs that are manufacturing this unit, they have done a lot of lab tests and they came to a very precise and correct list of parameters that can be changed. What we do in general is that we have some values, some parameter values that are, let's say, good for 90% of the cases, not 100%, but most of the cases we can cover with the standard parameters. And later, if the OEM wants, they can make some analysis and fix these values to be more efficient in terms of how long it will do and how often it will be done. So it can be improved, but it covers most of the cases.
Yeah, so this is something that I'd like to know because a lot of OEMs will be buying your equipment, putting in their equipment. They may change those parameters. So when a technician does that upload, that would be going with your default parameters at about 90%. 90% of the time that's going to work flawlessly. Even I'm sure 100% of the time it's probably going to work, but it's just not going to work as good as that fine tuning of the OEM. But what I would like to know is like, does it have to run for 2 hours at less than down to 25%? Is there an idea? Because when this is going to happen is when you're not there. Like this is low load situations in the middle of the night. The doors are shut, no products put in there, right? That's when this happens. That's when you run into this oil management ramp up.
Yeah. If I'm not wrong, it comes at 60 minutes running at speed below 45%, if I'm not wrong. So you will accelerate the compressor at 80%, something like that, for like 1 or 2 minutes. Just a rough estimation of parameters. but it's not something that will make it very unstable conditions, just to make sure that you are dragging back oil to the compressor.
Yeah, because you need oil at the compressor. And then as well, if you start logging in the evaporator, you're not going to get your heat transfer anyway. So you need this to happen both in both situations. You need oil in the compressor, as well as you need those pipes that not have oil in, so you get the proper heat transfer. Awesome. If you run into this, is there a certain numbers that will come up on the drive to say that, okay, we're in oil management ramp up feed, or is there anything that will let a technician know that that's happening?
Most of the controllers, it will pop up a message on the main screen saying status. Instead of compressor on, it will be oil booster or oil recovery procedure, something like this. Most of the socket comes with a message saying you are speeding up the compressor for some reason, and it will be shown over there.
Yeah, awesome. Yeah, because that's so important for them to understand, like, why is this compressor all of a sudden ramping up? I was just looking at it, and now all of a sudden it's ramping up. So give them an idea. And this is why you have to be curious. You got to keep your eyes and ears open as a technician in the field when you're servicing equipment like this.
Yeah, right. Most of the controllers now, it comes on the main screen saying speed of compressor, opening of the valve, and also the status. We will see on the inverter side, on the envelope side, that are zones like zone 1, zone 2, and it will say oil recovery zone, so we are recovering oil to the compressor. Talking about the famous envelope control, so I try to drag here and draw some images and try to show you what it is, the envelope control. So basically, here we have a graph with evaporation pressure and condensing pressure, and the correlation that will make the zones of operation. Like, as you may know, all the compressors, they have a minimum condensing pressure, a maximum condensing pressure rated by the OEM, by the manufacturer. So these are the limits in terms of condensing pressure. Also, for the evaporation side, there are the same minimum evaporation pressure, maximum evaporation pressure. So we start to draw where the compressor should work. So mainly, we should work inside the middle, not below the evaporation the evaporation pressure, not above the maximum pressure. And for the condensing, the same. We will add some, for example, maximum compressor ratio. So basically, when you have a very high delta P between pressure, evaporation, and discharge lines, we also have a limitation in terms of maximum current. So the motor is rated for some current, so you cannot overcome this threshold. So there is also a limitation on that. And also, as we discussed, mainly for the oil lubrication process inside the compressor, we need to maintain a minimum compressor ratio. So a minimum pressure differential between suction and discharge to make a pressure enough to make the oil going from the bottom of the compressor to the compressor chamber. So this is the limitation. And all of these things here in the middle, this white zone here in the middle, it is the main operation zone. This is where the compressor should work, like let's say 99% of the time. This is the safest zone for the compressor to operate. But as we may know, we should have some conditions where, for example, this could go bad, like the evaporator starts to frost too much, so the evaporation temperature in consequence starts to decrease, and we could come here. In this point, what we should do is the compressor starts to deaccelerate in order to push back the operation point to the middle of the application. The same for the maximum evaporation pressure, or as we know, MOP, maximum operation pressure. If we start to see a MOP condition, what we do is we start to accelerate the compressor and close the electronic expansion valve. We have some combined actions between compressor and the valve to make this bundle working always in the middle of the control. And this is the safest zone, and the software, the controller itself, will try to make the system all the time running inside the envelope conditions.
Okay, and that's super important. And this is what you want to understand about inverters and stuff. They're going to try to take care of issues that are happening, but they do not fix the issue, the mechanical issue. Because if you're getting up into that the red zone he has in the top, the maximum condensing pressure, If that condenser is super dirty, super plugged, you need to clean it. It only can do so much until it's going to trip off on high discharge pressure or high discharge temperature or discharge line temperature. And same with going into the minimum evaporator, just like Marcel said, you start to get a frozen coil. And if it's a frozen up coil, you have to go in and thaw that out. It's not going to fix those problems. So I'm assuming that what'll happen if it goes into the minimum evaporated pressure for a little bit, it will notify alarm. Is there alarm settings in the inverter where I can come in because the compressor's off because I get a call from say an end user and their cooler is warmed up? Is there alarm settings where it'll say minimum evaporator pressure to give them an idea of what's going on?
Sure. Every time you go out of the envelope, the controller will try to force you back for the center for like 3 minutes. So let's say that we are in the minimum evaporation temperature. For 3 minutes, the system will do all it can in terms of deaccelerating the compressor, opening the electronic expansion valve in order to force the operation point to the safe zone, let's say. If it is not possible, it will trigger an alarm, and this alarm will stop the compressor for like 5 minutes. It is a time in order to make an alarm, make the technician aware that we have a problem, and it will show you minimum evaporation pressure alarm. And after 5 minutes, it will start again. In order to avoid multiple starting ups of the compressor in a bad condition, after the 50th alarm in 1 hour, it will stop and will require a manual reset of the alarms. So it is for 5 times, the controller will automatically reset the alarm and try to come back operating. If for the 60th time in 1 hour, 1 hour period, it will stop the compressor and will require someone to go there and look and see what is happening. All of these will be analyzed by our alarm relay inside the unit. Inside the main screen, we'll have an alarm. If you have a monitoring system, it will trigger an alarm on your monitoring system. We do all we can in order to make customer or the maintenance team aware that we have a problem with these units.
So now everyone needs to remember that if this happens, and it doesn't matter what type of electronics, if it's this one or others, if something locks out, there's a reason to it. It's not the electronics that's an issue 99.9% of the time. There is actually something going on with the system, usually mechanical. Usually, if that system was set up and commissioned properly from day one, you don't have to go in and start changing all the parameters. You got to go find out exactly what mechanically happened. Did it lose charge? Is the evaporator frozen? Is the condenser plugged? Is the electrical coming loose? There could be one of many things, but if you get a lockout, don't just go and manual reset it right away to get it back up and running. Use your eyes, try to see what's going on, get your meter out, see if there's anything open, high pressure switch open, low pressure switch, whatever it is, to try to find a problem. Because if you do a reset and all of a sudden get back up and running, that might not happen until 2 days later. Have you experienced that doing support, Marcel?
Sure, this is the most of the out there. It is something mechanical that we need to pay attention, or a frosted evaporator, or a lack of water in this case, water loop units. We need to understand why is triggering alarm, not the alarm itself, but why it's the root cause that could be triggering the alarm. The alarm is just protection in order to avoid burning a compressor or breaking some other parts of the unit. It's just a preventive way to do not harm too much the unit.
Yeah, and that's so important because what I've noticed in all the field support I've done and the troubleshooting I've done, there's people out there that don't understand the technology, blame the technology. So don't blame the technology until you understand that root cause. And sometimes it takes a long time to figure this out. It could be a loose wire that you get there and it works. Sometimes you have to sit there and watch a piece of equipment for a couple hours, maybe even a couple days. It's not always the funnest part of the job. But when you find that root cause out and you figure it out, you feel like a champion. You're like, man, that's the exact problem and I fixed it. So take your time when you're troubleshooting.
Yeah. So just summarizing, basically what we have here is a complete control of the envelope of the application. We have a dedicated algorithm for oil recovery, and we can make all this information available online if you need for the IoT stuff because we have all the technical information. The expected outcomes is once we have a very stable condition, the temperature will be very stable because we will be adjusting the cooling capacity all the time. But more than the temperature, the humidity will be very stable. Every time that you power cycle a unit, the humidity inside the ambient will change very much. So if you have a constant evaporation temperature, we could have a very constant humidity. For medium temperature application, where we have exposed product like vegetables, for example, it makes a lot of difference in terms of shelf life of the product and the quality of the product when we are dealing with those.
I definitely agree with that. So in this system, is it an option to get like a humidity sensor, or is that included in your application? We'll talk about in a little bit.
Some of the applications could have a humidity control in order to adjust that, or just measuring needs. It is possible to, in some of the applications, to add humidity probe to control these stuff as an extra feature for the application.
Awesome. I do have a quick question for you. In regards to the EV opening to balance that pressure, because I know you said you can do it through the oil side as well, are you worried about liquid flood back for that time?
Generally speaking, when we have this kind of side of unit, it is not a big problem to just adjust the pressure because generally when the compressor stops, it could stop by just stopping the compressor or doing pump down. And during the pump down procedure, you make a big delta P. So injecting a little bit of refrigerant on the evaporator side, it is just making the pressure to rise up a little bit and make the compressor starting a little bit more smoothly. It's not a matter of being open for a lot of time with the compressor off. It's like for some few seconds just to make these adjustments on the pressure. So we are not worried because also the charge is very low.
Yeah, and I've seen that before too. Like these systems, very low charge, but you just want to get that pressure up. So the chances of getting there's always a little potential, but you open it up, the pressure goes up, it starts up, and then it just starts to run. So, but that's a good thing. That's something you should check. The person who asks, like when you're in the field, these are things you should check, especially if you haven't worked on a piece of equipment. This is all about testing and measuring your system, and this is how you learn. So if you ever come up to the system, even though it's going to tell you all the pressures and temperatures, you're probably on the drive or on the controller, you need to verify that temperature probe's reading accurately. As technicians out there, you need to verify that stuff. So important. Thank you for the question. It was great.
Oh, perfect. So just getting into the CO2 lineup, just to make some reference of capacity and cooling, we have compressors that are vertical and also horizontal ones with displacement from 3 to 10 cc's of displacement. They are the same model, but one is vertical and the other one is horizontal. I will show up the real envelope of these units so you can see that there are a few difference on the how wide the envelope could be.
Okay, you want to go back just for 1 second? So there's a lot of people that haven't not worked on twin rotaries. So what is that cylinder to the left side of the twin rotary compressor?
Yeah, these are a suction accumulator and noise reduction. So we can protect a little bit the compressor with a smaller suction accumulator just to make sure that we are not flooded too much the compressor with liquid back from our application. And also, it also has the function of reducing the noise of the refrigerant inside the compressor. So they have two different functions. Both of the models, this one and the other one has a smaller one, but both have the suction accumulator tank.
Okay, so in those is there any chance, like how does the oil get back to the compressor? Because I'm assuming you'd have, and I've seen inside different ones before, that you'll have a pipe up. So if any liquid does come back, like any suction accumulator, you don't get the liquid back into the chambers. Is there like a little hole in the pipe to meter back the oil, or how does that work?
Yeah, we have a small C curve on the bottom of this suction accumulator with a very calibrated hole, so we can make sure that we are always receiving some liquid that are in the bottom part of the accumulator, but not flooding completely. So most of the refrigerant will come through just the suction part that is on the top of the suction accumulator, and on the bottom we just have a small C pipe with a hole to make sure that we can recover this oil that obviously will not evaporate inside the cylinder. Yeah. Some references of capacity. So the bigger compressors, they are twin rotary. The smaller ones, they just have one chamber by the capacity we have, and the related design, if it's vertical or they are horizontal ones. They are quite similar between them.
So these compressors, go if you don't mind just going back for a second, those compressors, they would be already matched to your drives. Is that correct? So if someone wants to purchase, just say that twin rotary, the first one, 6 to 7 cc's, that will have a match already to it. And can they go into your software, Carel software, and we'll talk about this in a little bit, to find out that specific unit that is needed?
Yeah, we have some tables, cross-mat tables, with the compressors and inverters for each one of the models. And for each type of application, like if transcritical, for sure the current absorption is higher, so it is the standard models. And if subcritical applications, we can try to downsize a little bit the inverter if it's possible. So we can make some adjustments in terms of inverter matching according to the application of the customer. This is a very interesting point. These compressors, they are UL certified to run both in subcritical and also transcritical applications. And also in the UL, we have the match between inverter and compressors. So here as a reference, we do have a envelope zone for each one of the applications. So as you can see here, the vertical one, we have a transition zone a little bit wider than the horizontal one. So for some specific application like multi-DC, where we have multiple compressors, and we need this transition zone during the operation, we could use vertical compressors that they are a little bit wider in terms of where the compressor can operate. Here we have both the application for LT and MT. This line means subcritical or transcritical. For subcritical zone, we can operate both MT and LT. And for the transcritical zone, we can operate as transcritical or as parallel. If we need transcritical low temp condensing unit, we can have two compressors, one with low temp application and the second one as parallel, just to make sure that we can maximize the efficiency of the unit. So having the better COP.
Do you have software that you can plot this? They can plot the units that they're looking for the different applications?
Yeah, we do have a selection tool that is where you will input some values based on the cooling capacity, evaporation temperature, condensing or gas cooler pressure, and the software will indicate you the right capacity, the capacity it can have for that application, reach rejection, mass flow, and so on and so forth. So you can have an overview of the application of that compressor in that condition, both for the vertical or for the horizontal one.
I noticed that maximum discharge temperature is a little different on the horizontal one than the vertical one. What do you know what the reason is for that?
Yeah, basically by the limitation of the mechanically speaking, the vertical one is a little bit more robust than the horizontal one. So we accept a little bit higher temperature and a wider range of the application. But it's 10 degrees difference between one and other.
It's still way too hot. Either one of them, 120 Celsius or 130 Celsius, is still too hot. It's still too hot. You're running hot there.
Yeah, an extension here, as I mentioned, for transition zones. And talking about the applications, where we can apply this compressor and where Carel has already developed the software that can support these applications. These type of compressors are available both for the programming platform and for the parametric ones. It means that we do have some standard applications that can match these compressors for CO2, and also our customers, if they want, they can use our programmable platform in order to use our blocks to control these compressors and develop a custom application for their own, for what they need. One of the standard applications we have, it is the water loop solution. And this is one example of what we can do. It's a water loop condensing unit running at subcritical applications where we can use these kind of compressors, vertical or horizontal. In this case, it's a horizontal one. and you can use the available cool chilled water that you have in your installation to reject all the heat from the installation. So the idea here is that we have a very low height unit that you can place on the top of a showcase or on the top of a cold room, and you can make refrigeration circuit very close the condensing unit to the evaporator. So in this case, you can reduce refrigerant charge, you can maximize the efficiency, and you have a micro-distributed system. I put here some example. For example, a chilled water generated by propane chiller, for example, to be like 100% green. And you have an MT unit that can reach up to 3.5 tons. And also the unit for low temp application that can reach 2.2 tons. So we have solutions for both medium temperature and low temperature showcases or cold rooms that are running in the same unit. And in this case, we just have a water loop system with chilled water that can make it run. We can integrate into the HVAC system. Another approach is the HECO platform, that is the high efficiency condensing unit. Basically, here we have all the controller and the components in order to make a condensing unit with CO2, both subcritical or transcritical. The software can manage both of those applications. And also the HPV valve and the flash gas bypass valve in case needed. So we could manage both applications into transcritical systems. This is a schematic of the system. Basically, what we have for medium temp applications, we can manage both high pressure valves, bypass valves, and also the compressor for medium temp directly. And in case of low temp applications, we can manage the high pressure valve, the low temp compressor, and also a parallel compressor, just to make sure that we can reach higher capacities and maximize the energy efficiency. If we do this in a single stage operation, the COP would be very, very low. So we can increase this having two compressors connected in a booster mode. And last but not least, these compressors are also available to manage in a booster application or in a rack application. We can manage up to 6 compressors for MT plus 2 compressors for LT, and we can make a very higher capacity in a small footprint. As you can see, this sample unit has like 4 foot by 4 foot of area. So it's a small footprint area, and you can have a higher capacity solution with multiple compressors.
So that system there, just say that your size there would be 13 tons medium temp and 3 tons low temp in that one multi-DC booster rack. Is that correct?
Yeah, you can sum up both capacities. And here is an example. You are all the time, both compressors are running and adjusting it. As you can see, we are out of the envelope and the unit is trying to correct and fixing and pushing it back to the applications. All the time we are looking to the compressor safety and try to make sure that the compressor is running now in a proper condition. This is a RAD built-in and a RAD developed. It's not something that you need to develop by yourself. It's a RAD pre-built into our applications.
And who is your target for this? Would this be end users? Would this be contractors? Would this be other OEMs? Like who, for these equipment, this multi-system booster, multi-unit compressor booster?
Yeah, all of these are, Carel is a provider, it's a vendor for the components. We are not manufacturing a multi-DC booster rack, but we can provide the controller, the valves, the compressors, inverters, probes, and so on and so forth. So for this kind of approach, we are targeting, for example, OEMs that are interested in developing a new line of CO2 applications where they can maximize the efficiency for their applications.
Awesome. You guys put all the R&D in and you did all the work, and now it's able to help manufacturers fast track.
Yeah, right. We have a lot of content about natural refrigerant solutions. We have our website, hot site dedicated to natural refrigerant solutions, and there are lots of information about these individual applications and also about the compressors and inverters. If someone would like, all this information are available, and also this presentation would be available if someone requires. Our pleasure to share what we have done and the developments we are doing on CO2, mainly interest critical and also supercritical applications.
That is awesome. Why don't you stop sharing and just talk a little bit about, show us a little bit about the product in front of you there?
Yeah, sure. Here, what we have, I brought for the presentation is this is a CO2 supercritical unit that we have developed for the local markets, South and Central America, where we have the horizontal compressors and the whole system to be installed into a showcase or to a condensing unit. The idea here is to use a chilled water that could be provided by the HVAC units, the HVAC systems, or also here in South America, there are a lot of applications with secondary fluid like glycol for medium temperature. So we can get the benefit of having a glycol running into the storm and expanding with more points, with more operators with this kind of unit. This is a pre-built unit that we could supply. Carel has the same approach also for North American market with a small different approach with the unit. And here we do have, I brought you guys just to present the version of the inverter. This is a single phase inverter focused on OEMs with custom connectors for very quick installation procedure. For your knowledge, this is of the compressor. So both the vertical compressor, this is RY 100. This is our biggest 10cc compressor. And as you can see here, it's 1.5 hands. It's a very smaller compressor in terms of footprint. And also the vertical or the horizontal one that we have installed here. Just as a reference, this unit has like 1.5 feet of height. So it really can fit in everywhere you would like to install this kind of systems.
That is awesome. That is awesome. I want to thank you for taking the time to go through this. There's still lots more questions. I'd love to dive deeper technical on it, but I really enjoyed that envelope that you went through because that's so important. And it's cool that you have a controller that's monitoring that. And I think this is where we need to start to learn and continue to evolve as refrigeration professionals. As the technology grows, it becomes more sophisticated. And we want to understand how the sophistication in the controls work. I'm sure you have tons of documentations that you go to that Carel's website. There's lots of support for it. And this is one of the big things that I hear. There's nobody supporting the product. There are people at these manufacturers who want to help you, just like Marcel and his team and other people around the globe. They want their product to succeed. So they do support it. Marcel, I want to thank you for taking the time to do this and show us this product line.
Thank you a lot, Trevor. It was my pleasure being here. Everyone that needs any information, please reach me out. I'm available for discussing about CO2. I really enjoy this, and I really enjoy talking about refrigeration technology. So please just reach me out, and we can discuss a little bit more. Thank you again for the opportunity, and it was a great show. Thank you, Trevor.
Awesome. Yeah. So make sure, check the show notes. There's going to be links to the ones that Marcel talked about. I'm going to get the software links that he talked about, the selection tool. I'll have that in there, as well as share this with people that want to learn more about this. Maybe they haven't seen a product like this before and it's something that they're looking for, or maybe it's something that you're looking for if you're a manufacturer, just to help fast track your CO2 game, because this is the CO2 is happening. It's here. If this is the first time you're learning about CO2, reach out to the experts. And Marcel is one of them. Marcel, thank you so much for your time. Thank you everyone for attending CO2 Mondays and the Refrigeration Mentor podcast. See you later.
Hey, thank you for watching this video. I do hope it is bringing you a lot of value. If you are looking to grow and build your refrigeration teams and want them to learn CO2 refrigeration, head to the refrigerationmentor.com website, click to contact us, and let us know how we can build a culture around training inside your organization. Let's get a conversation going.